Hi, what the Kim, what the Kimmers, what the Kim buddies, what the Kim heads. I can't remember what else he says. All right, so this is the third episode, hopefully better than the last episode, because I learned a couple of important things during episode 2. Yes. I learned, for one thing, I learned that you shouldn't have the YouTube stream open at the same time that you're actually trying to stream, because what will happen is you'll start talking, and then 20 seconds in, you'll hear yourself start talking, and it'll really screw you up. Also, I learned that if you stop a Hangout, it's really hard to start another one up right away. At least it was last week. Obama was doing something on YouTube. That might have been it. I don't know. And also, I learned this actually in episode 1 that a microphone would help, but I haven't got a mic yet. I'm going to get a mic yet. I know that it sounds like crap. I'll get to it eventually, hopefully by episode 4. I couldn't do it this week because I had to start early. Normally I start on Thursdays. Today's Tuesday, if you're watching it after the fact. And so it's going to sound like crap for at least one more show, but hopefully it'll sound better soon. Hopefully it looks better now because I got a haircut. See? Which is another thing I've learned. I can't let my hair grow long if I'm going to keep doing this kind of crap. But anywho, so today's shoe, we're going to talk about naming compounds for General 1, and then a little bit later, we're going to talk about some colligative properties for you guys in General 2. And when hopefully I'll start doing them, start time stamping it once this show gets archived. And in case you just want to jump to whatever bit you want to look into or you're interested in, or you just don't hear me talk in between. But which is another thing that I'm starting to learn is that this helps. I don't know, if you don't want to hear me babble for a couple minutes, that's fine. You can do something else. But this kind of helps me make sure everything's set up. And plus, it kind of helps me get comfortable knowing that I'm talking to nobody. But at the same time, I could be talking to everyone. So, yeah, if you don't want to hear me ramble on, sorry. Just deal with it. Live shows are fun. All right, so anyway, moving on to General 1. All right. So, like I said, for naming compounds, oops, wrong one. And I did find out I could edit these in post, but I don't want to. I kind of like the rawness of it. Then I'm just too lazy to edit them after the fact. I don't have time either. You know. All right, anyway, here we go. Okay, so with naming compounds, or at least naming inorganic compounds, most inorganic compounds, they follow the same basic naming rules with a couple of tweaks here and there. By and large, most inorganic compounds are named something, something-eyed. So for ionic compounds, the first something is just the name of the cation. Because remember, that's how cations are written. Their formulas are written, cation, anion. The anion is usually just the name of the anion with an IDE suffix slapped at the end. Although we'll see later, that's really only true for monatomic ions. Polyatomic ions are a little different. And going back to, but just sticking with monatomic ions for now, as far as where you put that IDE suffix, for the most part, you're only dealing with about 8 common anions in Gen 1. You know, the halogens plus a few others. There might be some besides these 8, like carbon and hydrogen, that you might see now and then, but these are the main 8. God damn it. Somebody's at the door, but I'm not going to answer. All right. But anyway, these are the main 8. And after a while, you use these enough where you get used to where to put IDE. So again, but all the halogens, they're named with ene. Honestly, I think it's the Girl Scouts out there because it's currently January. So I'm gonna talk quietly, or not. But it's the whoever it was, they just screwed up my train of thought. The halogens, live shows are fun. They're all end in ene: fluorine, chlorine, bromine, iodine. So we just replace the ene with ide. For the four on the left, you kind of get used to where the IDE ends up going. Like, so nitrogen we call nitride because nitrogide just doesn't sound as nice. Same thing with phosphide, oxide, and sulfide. You learn pretty quick what sounds what. And for a lot of these ions, you kind of know their names already just from seeing them in the news or whatnot. So looking at an example like lithium fluoride. No, I already gave it the name. Whoever was at the door just really pissed me off right now. So with lithium fluoride, almost did it again. With LiF, we would name it, as I already said, lithium fluoride. Na2O, we would call sodium oxide. And Mg3N2, we would call magnesium nitride. And notice for these simple ionic compounds, this is all the information you need. Is just name of the cation and name of the anion with the IDE suffix slapped in there. You don't need any other information because what you see in the name is all the information you need if you want to go the other way, if you're given the name and you want to figure out the formula. So looking at the last one, for example, all you need to know to get the formula for magnesium nitride is the name magnesium nitride. So with magnesium, you know that magnesium is a +2 ion usually, as we talked about earlier in this chapter. Nitride is the name we give nitrogen, which is in group 5. So those guys usually have a -3 charge. And from there, you do the crossover method and you get the formula Mg3N2. So these three, though, notice they're all constant charge ions. They're from either group 1, group 2, or group 3. Actually, 2 are from group 1, one's from group 2. These are constant charge elements. Now, they only have one common charge when you find them in nature. For variable charge elements, this name isn't going to work as it's given. Take the two common compounds of copper and chlorine. So the compound on the left, following the same thing we did for the previous 3 compounds, we'd call this guy copper chloride. But the guy on the right, we would also call copper chloride. And you can't have 2 names or one name for 2 compounds. It would be too confusing. If procedures said to add copper chloride to your solution, you won't know which one to pick. So there's a couple of ways that we do it. There's an old way that involves Latin suffixes, and it's kind of outdated, so I'm just going to skip it. And you may or may not need to know it in your class. For me, I talk about it a little bit in the book, but we don't use it at all. The modern way to name this compound is to put whatever the charge of the cation, or whatever the charge of the cation is, you put that as a Roman numeral in front of its name. So for the guy on the left, copper must be +1, because remember, ionic compounds are neutral overall. Chlorine is -1. So if they add up to 0, that 1 copper has to be +1. So we call it copper 1 chloride. The guy on the right, copper must be +2 if the charges are going to balance out. So we call that guy copper 2 chloride. So if you go from name to formula, like with iron 2 sulfide, Again, we know that iron, we're talking about the cation, the +2 cation of iron. Sulfur is always -2, or usually -2 in nature. Put those two together, you get Fe6, or Fes, excuse me. Iron 3 sulfide, on the other hand, would be made up of iron 3 ions and the same sulfide ion. Put those two together, we get Fe2S3. And remember, we only use these Roman numerals when the metal is a variable charge element. Going back to those previous three, we don't have to call lithium LiF lithium 1 fluoride, the second one sodium 1 oxide, or the third one magnesium 2 nitride, because these are all constant charge cations. Lithium's always +1 as far as we're concerned, and sodium's always +1 and magnesium's always +2. So adding the Roman numerals will just be filler, and we try to keep the names as simple as possible. Now, as far as polyatomic ions go, like I said earlier, this IDE suffix we only use for monatomic ions. If it's a polyatomic ion, you just use whatever the name is, whatever name you were taught. So phosphate, for example, is PO4 3-. We're not going to add the IDE suffix to that for really one simple reason, and that phosphide is the name we give the monatomic ion of phosphorus. So, for example, this guy we'd call potassium sulfate. This nickel nitrate compound we would call nickel 2 nitrate, because nickel is a variable charge element. And this compound, NH4, is the polyatomic ion ammonium. ClO4 is perchlorate, so we would call it ammonium perchlorate. And notice for ammonium, it still follows the rule before. Whatever the cation name is, it's just the name of the cation. The only difference between these three and the previous examples is we don't add the IDE suffix to the polyatomic ion name. You just use the name as you were taught it. So those are ionic compounds. For covalent compounds, they follow the same basic somethingide rule as before. And the first element is just the name of that element. The second element is we use the IDE suffix. And later on, when we get into structures at the end of the semester, or typically the end of the semester in the traditional format, you learn why the first one's written first and the second one's written second, because really they're both non-metals. Ionic compounds usually metal, non-metal, if they're both monatomic ions. But there's a reason the first one's written first, but we'll talk about that down the road a bit. So again, for now, it just follows the same general, somethingide formula. But with covalent compounds, we add prefixes to the two names for reasons we'll see in a minute. And the prefixes, most of those you're pretty familiar with. Like di is 2, tri is 3, penta 5, pentagon, octagon, all you UFC fans. The two oddballs are usually tetra, or new ones, and hepta. But most of the others, you're familiar with one sense or the other. Deca, decade. One note though, for mono, which is our prefix for 1, we don't use that one all the time. It's only used some of the time, really rarely in General 1. Only a couple of cases where you see it used, and we basically never use it more or less for the first element. So for the most part, we don't use mono that often. If we do, you usually see it in those rare cases like carbon monoxide, where we use it for the second element. But for an example like PCl3, we would call this guy phosphorus trichloride. Again, we don't bother with the monophosphorus. If you don't see a prefix, the one's implied. Kind of like you were taught when formulas themselves were introduced. You don't write a one subscript. If you don't see it, it's the one's implied. But another form of phosphorus chloride is 1 phosphorus and 5 chlorines. Because remember, covalent compounds are made up of nonmetals, and nonmetals can combine in a bunch of different ways. And unlike variable charge elements, there are no charges here, so the Roman numeral trick isn't going to work. So that's why we use prefixes. So this guy we'll call phosphorus pentafluoride, or pentachloride, excuse me. A couple other examples. SF6, 1 sulfur, 6 fluorines, we would call sulfur. Again, we don't worry about monosulfur. The one's implied if you don't see a prefix. Hexafluoride, because there are 6 fluorides. If it's S2F10, now we add a prefix in front of sulfur. Prefix for 2 is di, so it'd be disulfur decafluoride. And when you're going from name to formula, there's no crossover kind of mess. I mean, disulfur just means 2 sulfurs. Decafluoride means 10 fluorines. So going from name to formula is actually, I think, a little bit easier for the covalent compounds, because you're just kind of writing the formula as you see it in its name. So, like I said at the beginning, notice overall it's the same something I formula or system for naming these inorganic compounds. But again, there are a few tweaks. For one thing, if the metal in an ionic compound is a variable charge element, you use the Roman numeral. If the anion is a polyatomic ion, you keep the original prefix. Don't add IDE. And for covalent compounds, you use prefixes to note how many of each you have in the formula. And you only use the prefixes officially. If you ever look on food labels, it doesn't, people don't always stick this rule in industry. But officially, prefixes are used only for covalent compounds. And going back to our earlier examples, because I forgot to make a slide. Yeah, we don't have to call this compound, the middle compound, disodium oxide or monoxide, either way. Or we don't have to call the one at the end trimagnesium nitride. Because as we saw before, with magnesium nitride, all you need is what you see in the name. You just need to know it's magnesium is the cation, nitride is the anion, and you can look on the periodic table to find the charges and do your crossover method to figure out the formulas. So that is naming inorganic compounds. And we only do really inorganic compounds for the most part in Gen Chem. Some people like to do organic naming at some point in the general sequence. I usually don't. And I'm not going to talk about it now just because, well, for one thing, I'm not ready to do organic on this show yet. We'll see. If I'm season 3, I might. We'll see. Let's just make it through the first season. But also, too, I mean, I did, what's the timestamp so far? I don't see it on here. But it's been like, what, 10 minutes? It took me like about 10 minutes to go through inorganic naming, sum it up. I would barely get through just naming simple organic compounds. Inorganic is much more involved. And usually in organic chem, oh, I blanked. Oh, there we go. Usually in organic chem, crap, did I just lose everybody? No, I'm still here. Okay, I had a blackout. I was worried that was going to happen sooner or later. Screen just went black on me, but I think you're still there. If not, I really am talking to myself. But now it looks like I'm still going. All right, one day it might crash because something's getting old. I need to do a computer update. And also I'm on Wi-Fi. So, but Google Fiber is coming to Raleigh. But anyway, organic. It would take a long time to do. And usually in organic chem, what they do is they just kind of introduce it in pieces. So no organic today. And if you take in Gen Chem, most of you won't have to worry about it for another, God, oh, did it again. another semester or two. All right, and just like that. If it ain't one thing, it's the other. All right, live shows are fun. All right, so let's move on to Gen 2 before this thing implodes on me. All right, where am I at? Let me go to Word. So with General 2, and we're going to talk a little bit about colligative properties. And with colligative properties, the four you usually learn in General 2 are vapor pressure, boiling point, elevation, freezing point, depression. Oops, I don't know what I was trying to spell there. I don't know. Yeah. Depression and osmotic pressure. I know, no fancy slides for General 2. Sorry, guys, I didn't have time to do slides for both. But for the most part, as far as calculating these properties, and to back up too, remember colligative properties, they're identified as, you know, being only affected by the amount of, by the amount of solute present. It doesn't matter whether that solute is an ion, a covalent compound, or an organic solute. It's just how much of that stuff is dissolved. And the calculations you do with these colligative properties, there are four different equations, one for each property. But for vapor pressure, it's usually written this way. Freezing point depression is written this way. This is the, whoops, left out malaleity. Boiling point elevation, the equation is usually written like this. And osmotic pressure is, oops, that's the wrong one. It's C, sometimes it's M, CRT. So all four of these, they're different equations, but all four colligative properties equations have some things in common. I mean, to calculate each property, you're basically multiplying the concentration by some constant value. You know, for, oops, I left off that. For vapor pressure, you're multiplying the concentration as a mole fraction by the vapor pressure of the pure solvent, which is this P naught here. For the two delta T's, your boiling and freezing point elevation, you're multiplying the concentration as molalities by two different constants. And by the way, freezing and boiling point, this is the only reason we bring up molality at all, because in all the things that I run into in chemistry, you know, everything I've taught, at least in Gen Chem, I've never seen molality anywhere else but here. So this is the only reason we teach it, because we still use molality to teach boiling and freezing points, elevation and depression. And for osmotic pressure, is concentration, and you multiply it by a couple of things, actually the gas constant and the temperature. And because of time, we're only really going to get around to doing the first three. I'm not going to have time to really get into osmotic pressure. But let's say, for example, that you have a solution that is, oops, $50 grams of a compound called ethylene glycol, which has the molecular formula C2H6O2. It's an organic compound, and you might recognize it as the main ingredient in antifreeze / coolant, although they use other things these days that are less toxic. I think it's still around in some places though. Let's say you have a solution where you have that solute dissolved in 150 grams of water. So first off, let's try to find the vapor pressure. And for my students, you'll notice this is the same example I use in the book, just because I didn't feel like coming up with a different example. Also, too, I was short on time this week because I'm starting early. But it's still a good example. So again, vapor pressure. Oops, actually, I gotta say vapor pressure. We gotta include the temperature at 25 degrees. So vapor pressure, it's mole fraction with respect to the solvent, multiply the original vapor pressure of the pure solvent. And at 25 degrees, water, pure water has a vapor pressure of 23.8 millimeter mercury. So the main thing we have to do to figure out this colligative property is calculate the concentration. So to calculate the mole fraction, again, it's like any other fraction, part divided by whole. We just don't multiply it by 100 because that would make it a percentage. We just want a fraction. And the part in this case is water. So we want to know the moles of water by the total moles of the solution. I'm trying to start a new page. What are you doing? Page break. Oh, that's why I didn't. I don't know. Live shows are fun. So, pen. So the first thing we need to do is take these two masses that are given and convert it to moles. So ethylene glycol, if you calculate its molar mass, it is 62.07 grams per mole. And I'm just shorthanded in EG because I don't feel like spelling out the formula, which is allowed. So that means that those 50 grams of ethylene glycol is 0.806 moles. And in that 50 grams of water, using water's molar mass of 18.02 grams per mole. Oops. Oh, I did it here too. Multiply. I'm going to blame whoever knocked on the door. They threw off my mojo early in the show. Doggone it. It is 8.32. So again, we're looking for the mole fraction of the solvent, not the solute. That's an easy place that students get tripped up because this is really the only place in this chapter where you're actually calculating the concentration with respect to the solute, which most times, is with respect to the solute. But in this particular case, it's with respect to the solvent. You'll see why once we finish up the calculation. So it's 8.32 moles water divided by the total. Got a little crooked. Which gives us 0.912 as our mole fraction. And again, it's a fraction, so fractions are unitless, because unit-wise, everything dropped out. So the vapor pressure of this solution is going to be that mole fraction multiplied by 23.8 millimeter mercury. Which is 21.7 millimeters of mercury. And if you look closely at the equation we just performed, or the calculation we just did, really all we did was a percentage calculation. Because in this solution, 91.2% of the moles in that solution are solvent particles. So Raoult, the guy this equation is named after, we call this Raoult's law. Now, what he found out was that, as the percentage of solvent particles drop in the solution, so does the vapor pressure. It's pretty much a direct proportionality. So that's why we have to calculate it, the concentration with respect to the solvent in this one case, because we're just really doing a percent calculation. So with, oh, it keeps doing that. Let's do that. So that was the vapor pressure. Let's take this same solution. And calculate the change in boiling point. So again, the boiling point elevation, as the name implies, is when you go from a pure solvent to a solution, the boiling point should increase. That's why ethylene glycol is often used as a coolant, because it increases the boiling point of the water that's running around in your radiator. So again, the equation we're going to use is this constant Kb multiplied by the concentration, written as a molality. And Kb varies from solvent to solvent. And in the case of boiling point elevation, Kb is equal to 0.512 degrees per molal, or mole, but I can't say that very well. So a minute ago, 50 grams of ethylene glycol is 0.806 moles. 806 moles. And to calculate the molality of the solution, you just take those 0.806 moles divided by the mass of the solvent. I almost said solid, but for some weird reason it's written in kilograms, or calculated in kilograms, which is why molality is such an odd unit. Most concentrations is per solution. This one's per solvent. It's a very odd concentration term. But that gives us jumping ahead. Nope, I'm right. 5.37 molal. Or again, mole. I can't say mole though. I have to think about it. I don't know if it's actually, I don't know if it's said molal or you say just like molar, but mole, just I get to mole mush mouthed. So anyway, that change in boiling point should be that constant multiplied by the molality. Notice unit-wise, the molality term drops out, and we're left with 2.75 degrees as our change in boiling point. And remember that boiling point is an increase. So if we were looking at pure water, whose boiling point is about 100 degrees, this solution should have a boiling point that's somewhere around 102.75 degrees. And if you wanted to calculate the change in freezing point, oops, it's more or less, it's pretty much the exact same calculation as boiling point or boiling point elevation. We just have a different value of K. Again, it varies from solvent to solvent, but for pure water, the Kf is 1.86 degrees per, however you pronounce them. So it's the same solution. We just calculated the molality to be 5.37. So you take that same molality and now you multiply it by the freezing point constant. And that gives you 999. So, which is a depression. It's going to decrease. So if pure water has a freezing point of 0, the change in freezing point should be about negative 9.99 degrees. Or the new freezing point will be that. But for all three, notice that they're really similar calculations. You're just multiplying the concentration. In some cases, it's a molality. In other cases, it's a mole fraction. And you're multiplying it by some value, either the pure freezing, the pure vapor pressure, or some constant. But the first thing you have to do in all three cases, and four, because the same thing is true for osmotic pressure, is to figure out the concentration.